Well, again, I'm Mr. Hyper, welcoming you. This physical chemistry lesson, our last lesson of phase equilibrium. And in this lesson, we are trying to talk about the phase diagrams of eutectic mixtures, which question appears to be kind of tricky for students. But let's see the logic behind these questions. We are beginning with a question of explaining how phase diagrams for solid liquid mixtures or the eutectic mixtures are obtained. So we want to know, how do we obtain the phase diagrams? How do we obtain the phase diagrams? So here I'm going to, this is a general question, so let's first answer it generally. Then after answering it generally, give a specific question which appeared some time back, and we also see how we can manage it now. For this case, when we are to explain how phase diagrams are obtained, we first plot the cooling curves. So cooling curves. For molten mixtures of various compositions, but equal total mass are first plotted. Various cooling curves for molten mixtures of various compositions, but equal total mass are first plotted. So these cooling curves give arrest points. These give the arrest points. These give arrest points for these mixtures. The arrest points, we mean the freezing points. This give the cooling curves give the freezing points. So this give the freezing points for these mixtures. After getting the arrest points, then the temperatures corresponding to the arrest points for a number of mixtures are plotted against composition of mixtures obtain the phase diagram. So we're saying that we first plot the cooling curves of various compositions, then we get arrest points, and the temperatures corresponding to these arrest points, or the freezing points, for a number of mixtures are plotted, and we come up with the phase diagram. We are going to look at how we can come up with a phase diagram. And sometime back, I think we're back 2019, they brought this question as this very part which I've done. They were saying, briefly describe how a phase diagram of biphenyl and naphthalene can be determined in the laboratory. How a phase diagram of biphenyl and naphthalene can be determined in the laboratory. So, like the way we've said, if we are to obtain or determine the phase diagram of biphenyl and naphthalene, they form an eutectic mixture. So if we are to determine this, what we do, we shall get mixtures of various composition of solid naphthalene and biphenyl, and we prepare them. So the first step would be mixtures of various compositions of solid naphthalene and biphenyl are prepared. After preparing these mixtures, we heat each mixture. Each mixture is heated separately. Remember, we are dealing with a solid, so by heating a solid, it will melt. So each mixture is heated separately until it melts. But remember, we brought cooling curves, so we have to let each mixture cool. So each mixture is allowed to cool. Each mixture is allowed to cool while stirring. And a constant temperature at which it freezes is recorded. So now we get the arrest point in that case. So we shall keep getting the arrest points at different compositions, right? Now, after recording that temperature, okay, the melting point of pure naphthalene and pure biphenyl are determined in the same way. Then a graph of melting points against composition is plotted and a phase diagram drawn. So that is how we obtain the phase diagrams. So initially you have the mixture of solid substances, but for you know that to obtain the phase diagram for an eutectic mixture, you plot a temperatures against composition. So since we have various compositions of these solid substances, by heating them, they are going to melt. As they melt, allow them to cool, because in our previous general question, we saw that we plot cooling curves. So we shall allow it cool until a freezing point or a constant temperature at which it freezes is determined. After determining the freezing point, then you can get the melting point using the same procedure. Then you plot a graph of melting points against composition, which will give you a phase diagram once connected. So this is a very, 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 very good question. It was carrying 3 marks. It's a paper 2 exam. We are going to do the whole question as we proceed. So that is what we are specifically having. So now let me take you to how to construct a phase diagram and how to describe, okay, how to describe the changes that do take place, okay, how to describe the changes that do take place. There are very many questions that one can do, very many of them, but we are going to do what we can. So let's look at constructing a phase diagram of tin and lead mixture. Constructing a phase diagram of tin and lead mixture. Of course, from the previous statements about the question of biphenyl and naphthalene, here still we are going to get pure lead and pure tin. We heat them separately until they melt, okay? Then each molten mixture will be allowed to cool and the constant temperature at which they freeze is recorded, okay? Then mixtures of various compositions of solid and tin, of solid lead and tin are also going to be prepared, and each mixture also heated separately till they melt. Then the temperatures corresponding to the freezing points are going to be plotted against composition, and we shall obtain the following phase diagram. I'm assuming that we already have the results of the melting points. So I'm plotting, we are going to do one question with the values and we see what we come up with. So we are having this. Here is temperature. Here is temperature. Degrees Celsius. Here we are having 0%, and here we are having 100% by composition. You are saying that this is the composition of tin. This is the composition of tin. So having something like this and this. So here, if I call this on my point B and I call it on my point C, this is 232. Then this is the temperature 183. I'm going to define for you these stages. Then this is 327, right? And naming these. Of course, I'm assuming I'm just assuming the values. So that is what I'm having. Then naming this. This is solid lead plus solid tin. This is solid tin and liquid mixture. Then this is solid lead and liquid mixture. And then this is our liquid mixture. So as I've told you, we're going to have a general question, an examination question, and we see how to go about it. Looking at this, we have got this point B, and this point B is what we call the eutectic point. So point B is the eutectic point. Okay. And we are going to find out that the eutectic mixture at point B, it has got 64% tin, okay? And the remaining percentage is for lead, which is 36, okay? So this diagram generally shows that addition of tin to molten lead results into the lowering of freezing point of lead. The moment you're having a certain substance and you add another, then you are lowering the freezing point of the former. I described that when we were looking at the introduction, we are introducing this. So as the mixture is cooling, okay, as the mixture is cooling, you are seeing from this, as the mixture is cooling, pure lead will crystallize out, because here we are having solid lead and liquid mixture. So lead is solidifying out or is crystallizing out, okay? So the liquid mixture becomes richer now in tin, okay, as more lead crystallizes out, and hence the freezing point of lead keeps reducing. What am I trying to mean? Initially, you're having the temperature as high as this 327, but as the liquid mixture is cooling, because this is the liquid mixture, as the liquid mixture is cooling, and as lead is solidifying out, all right, as lead is crystallizing out, then it is the mixture is getting less richer in lead and more rich in tin, okay? So the temperature, rather the freezing point of lead keeps decreasing, okay? And a certain temperature T is reached where both lead and tin crystallize out of the liquid mixture. That is what we call the eutectic point. And this temperature remains constant until all the liquid has solidified. So the temperature, the freezing point of lead keeps reducing until point B, which is the eutectic point, corresponding to this eutectic temperature, where the whole substance has solidified. Actually, you're going to find that the method of describing the shapes of eutectic phase diagrams is very uniform throughout and the easiest, okay, as we proceed. Now, line, what I may call, if I say this is my A, this is my point A, you're going to find out that line AB shows the variation of freezing point of lead as tin is added, okay? AB shows variation of melting point, and variation of freezing point of lead as tin is added, or lowering of freezing point of lead as percentage of tin increases, because the freezing point of lead is decreasing as we are getting the composition of tin increasing. As the composition of tin increases, then the percentage, rather than the freezing point of lead, decreases. So BA, now when you went to BA will show the freezing point of lead as the percentage of tin is reduced, because when you're going now this side, the percentage of tin is reduced. Then BC, point BC shows the variation in freezing point of tin as the percentage of lead is reduced, because the freezing point, here we are having the freezing point of variation of the freezing point of tin, but as we extend, or as the composition of tin increases, the one of lead reduces. Or one can call the increase in melting point of tin as concentration of lead decreases, all right? Then when you're coming now, CB, okay? CB will show variation of freezing point of tin as lead is added, because when you're coming this side now, you are going to the side of lead, you are increasing the composition of lead. Now, the phases at point B are solid lead, solid tin, and a liquid. At eutectic point, we've got 3 phases: solid lead, solid tin, and then the liquid. Now, the main important question that comes here is when they ask you to describe the changes that will take place when the liquid mixture of that system containing like 40% tin is cooled from 400 degrees Celsius to 100 degrees Celsius. They can give it 5 marks, and they tell you to describe the changes that do take place. Okay, so let's describe the changes that take place when a liquid mixture of this system containing 40% tin is cooled from 400 degrees Celsius to 100 degrees Celsius. Let's see what happens if 40% of tin is cooled from 400. But remember, on my diagram, I have 327, but the liquid mixture is being cooled from 400 degrees, and we are considering 40% tin. So what you do, you come and locate the 40% of tin, and then you hit it at the graph. You correspond it to the graph. Maybe I can call that one point Y. I just named it area, but it is cooling from a certain temperature, 400, which is not part of the graph. So that's why my line is extending from somewhere, from X at this point. So now what happens is the moment we cool the system containing 40%, we are going to say that the liquid mixture containing 40% tin cools without change in phase along XY. There is no change in phase along XY. So the main important note you're going to put is that the liquid mixture containing 40% tin cools, it cools without change in phase along XY, okay? And up to this point Y, lead begins to solidify out or to crystallize out. So, but from somewhere, it cools from 400 along XY up this point Y. Okay, of course, with a fixed composition up to this point Y, where solid lead begins to crystallize out. All right, now as lead solidifies without with the further cooling, all right, the liquid mixture becomes more saturated with the tin, and the freezing point of lead is further reduced. Because you are increasing the concentration of the composition of tin, but the one of lead is decreasing, right? And above all, introduction of tin into the system decreases the freezing point of lead. So what am I trying to mean? As lead solidifies out on further cooling, the liquid mixture becomes more saturated with the tin, and the freezing point of lead is further decreased along YB. Up to the composition of the eutectic B, where you can easily determine the composition of tin. So this is the eutectic point B. Now, at B, you can tell the temperature, which is the eutectic point. At B, the temperature remains constant, and both tin and lead solidify out together until all the liquid has solidified. Okay. Now, further cooling below this temperature results into no change in phase of the solid mixture formed. Further decrease of temperature below this, there is no change in phase from solid. So just as simple as this, just tell me that the liquid mixture cools without changing phase along XY with fixed composition up to this point Y, where lead begins to crystallize out. As lead solidifies out with further cooling, the liquid mixture becomes richer or becomes more saturated with the tin, and the freezing point of lead is further decreased along YB. After the composition, you can define it of eutectic at B, which can be defined as 64% tin. And at point B, the temperature remains constant, and both lead and tin solidify out together until all the liquid has solidified. But further cooling below 183 or further cooling below the eutectic temperature has got no change, has got no effect on the phase of the solid mixture we are dealing with. So I'm going to give a general question, and we do it, then we see how best it can be attempted, how best it can be attempted. Okay. This question, let's see how it can be attempted. The first part was defining the eutectic temperature. We covered that in our previous first video. So question, let me call this my part A. The melting points of mixtures of different compositions of cadmium and zinc, are shown in the table below. So we are having percentage of zinc, and then we are having the melting point of tin. Oh, no, not defined. Melting point in degrees Celsius. So we are having 0, 321. We are having 10, 295. We are having 17, 270. We are having 30, 305. We are having 60, 360. We are having 100, 491. So Roman 1 is draw a well-labeled diagram a well-labeled melting point composition diagram. Melting point composition diagram for the cadmium zinc mixture. For the cadmium zinc mixture. That is part 1. 2, explain the phase changes which would take place if a liquid mixture containing 5% zinc was cooled to 250 degrees Celsius. All right, then part 3. $200 grams of the liquid mixture of composition 5% zinc was cooled to 275 degrees Celsius. Determine the composition of the remaining liquid mixture at 275 and calculate the mass of cadmium in the remaining mixture at that temperature. This was taking 5 marks. This was taking 5.5 marks. And this is taking 5.5 marks. So generally, as I've told you, these questions, they can easily be excelled in after you having gotten a general idea about them. So let's try looking at it and we see. So we are given percentage composition of zinc, right? And at the same time, we're given the melting points. Okay, so now it's a matter of plotting. After plotting, we join and then we start describing. So let's have a question noted first. And then we see how we can come about it. How do we overcome this problem? Okay. Okay, so now it means that when the percentage of zinc was 0, and you have the melting point as 321, it means that at 0 composition of zinc, we have 100% of cadmium. Okay, so it would imply that 321 will be the melting point of cadmium. Let's see. Plotting. Of course, I'll put something simple in that I want to describe with all the information still here. So, of course, the first paramount thing is to give a title to your graph. Melting point composition diagram. Write full words, melting point composition. Melting point composition diagram for cadmium zinc mixture. Then here we have 0. We can say 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. So this is the percentage of zinc. And here, since I'm moving up to 490, I can use 50, 100, 150, 200, 250, 300, 350, 400, 450, 500. So this is the melting point in degrees Celsius. Now, plot. At 0, we have 321. Let me say, maybe it's here. Put a dot and a circle. Then at 10, we have 295. At 10, we have 295. That is close to 300. Somewhere like there. At 17, we have 270. Maybe somewhere like here. Be accurate. At 30, we have 305. Maybe somewhere like here. Then at 60, we have 360. Maybe somewhere like here. Then at 100, we have 491. At 100, you have 491, maybe somewhere like here. So join these points. That is what we are having. But it is at this point that you can draw your line . Of course, here you can easily determine the temperature. You can easily determine the eutectic temperature here. Then we have to label this. If you leave it like this, you can get like 1.5 mark. So at this point, you can read of the composition of the eutectic mixture. By what percent of zinc? What is the composition of the eutectic mixture? So here, this is eutectic mixture. It means that if it is like 15% zinc, then it will be 85% cadmium. Okay. And at 0 degrees Celsius, we say that this one here will be the melting point of cadmium. This will be melting point of cadmium. You have to label in full statements. Melting point of pure cadmium. This is the eutectic mixture. Maybe 15% zinc and 85% cadmium. Avoid being inaccurate. Don't mention this. But here we have our solid zinc plus solid cadmium. Then at this point, we have solid zinc and solid and liquid mixture. Then here, this point here, this triangle, call it this area, this region, we have solid cadmium and liquid mixture. Then entirely here, we have liquid mixture. Here we have the liquid mixture. You can label in capital letters or any. Here at 100%, this one gives us the melting point of pure zinc. At 100% compression of zinc, we have melting point of pure zinc. At 0% of zinc, we have 100% of cadmium, therefore the melting point of pure cadmium. Okay, of pure cadmium. So this is where our 5.5 marks go. As simple as this. As simple as this. Then now, when we are to explain the phase changes that would take place if a liquid mixture containing 5% zinc was cooled. 5% of zinc. So what you have to do, if 5% of zinc is cooled, you have to come here, you look for 5% of zinc. If it is maybe here, correspond it up to the curve, up to the graph. Maybe I can call this one my point L. And I can call this one my point L. Then I call this my point maybe M. Okay. Then I can call this one maybe my point P. So now they want me to explain the changes if 5% zinc was cooled. Now, it means they have not said from a certain temperature, no. It was just cooled up to a certain temperature. If they said from a certain temperature, like maybe 500, we were going to come from this side of 500 up to the graph. But because they have said 5% of zinc was cooled up to a certain point, so we shall say, this is maybe my point L. So I will say that the mixture cools up to, you read of this temperature and mention it, up to, maybe actually if you have drawn it well, you can get 310. Cools up to 310 degrees Celsius. which is my point L, up to point L of 300 degrees Celsius without change in phase. Without change in phase. Without change in phase. That one takes place without change in phase. Okay. Now, at 310 degrees Celsius, or point L, at point L, okay, cadmium begins to crystallize out. Cadmium begins to crystallize out. At point L, cadmium begins to crystallize out. But the composition of zinc is increasing. All right, the composition of zinc increases, causing a further decrease in freezing point, a further decrease in freezing point along LM, a further decrease in freezing point along LM on the curve. Or one can change this statement here. One can replace it with, as cadmium solidifies out, as cadmium solidifies out, right? Of course, with further cooling, as cadmium solidifies out with further cooling, what takes place? The liquid mixture becomes more saturated. The liquid mixture becomes more saturated with the zinc, and the freezing point of cadmium is further decreased, along LM, right? Along LM, along LM, yes, along LM. Then now we talk about a point M. At point M, zinc also begins to solidify or to crystallize out. In solidify or to crystallize out. All right. All right. It begins to crystallize out. Very interesting. Now, at this point M, the freezing point or the freezing temperature and composition remain constant. The freezing point, the freezing temperature and composition remain constant, all right, until all the liquid freezes, until all the liquid mixture does what? Freezes. Thereafter, because they told us to describe when it was cooled up to 250 degrees Celsius. So thereafter, the solid mixture cools the solid mixture cools up to the temperature you are told, up to 250 degrees Celsius, without change in phase, without change in phase. Cools without change in phase. So that is what we are having. It cools without change in phase. Then the last part of the question, was asking us that 200 grams of liquid mixture of composition 5% zinc was cooled. Now, the percentage that was cooled to 275 was they're saying 200 grams of liquid mixture of composition 5% zinc was cooled. So to 275 degrees Celsius, that is the last part, but I'm going to fidget it and it fits there because I need this diagram. Now what we do, we are going to check out for the composition of the liquid mixture at 275. Okay. At 275 degrees Celsius. 275, one can get it from somewhere like here. We just need a composition. So actually, when you check out for 275 degrees Celsius, maybe you're going to actually get composition. And that composition will be for cadmium this side because we are this side of cadmium. So, no, sorry. We are looking at this scale is for zinc, the percent of zinc. So at 275 degrees Celsius, the liquid mixture has got 16% zinc. But then the question says 200 grams of liquid mixture of composition 5% zinc, meaning that the mass of zinc in the liquid mixture before freezing, mass of zinc in the liquid mixture before freezing will be equaling to 5% of 200. Because the whole mixture of the whole liquid mixture has 200, but with 5% zinc. So this one will give us 10 grams. But remember, the question is determine the composition of the remaining liquid mixture at 275. Right. So at 275, the mass of zinc is 10. But now, if we are to get the mass of cadmium in the remaining liquid mixture, we are going to let it be maybe X. Let mass of cadmium be X grams. So if the mass of cadmium is let to be X grams, and I already have the mass of zinc, all right? It means that to get the percentage of zinc, to get this 16% of zinc in the whole mixture, I'll be having the mass of zinc over the total mass of the mixture, over the total mass of the liquid mixture, which will be X plus 10 times 100. That one should give me 16%, which is the mass of, which is the percent of zinc. Okay. If I need a 16% of zinc, I'll get the mass of zinc over the total mass of the mixture. I multiply by 100. That is when I will get the percent of zinc. So this one will give me the value of X, which is my mass of cadmium. And I want you to calculate and see if you come up with 52.5 grams as the mass of cadmium. So that is it. I'm going to add you like one question, but the topic is done like this. Let's see how it goes. Thank you for listening. I'm going to add you like one more question. I do it for you. Then I give you one other question for you to practice on your own. Good time.